welcome back. I had a bunch of questions about the homework, and I realized that actually I hadn't added the assignment to Elms yet, so now you can actually submit your first homework to Elms. I put the due date as Monday at midnight instead of today. That'll give you a few more days to have a look at it. And again, if you have any more questions about it, you can email me and let me know. I'd already heard from a few of you about it. And I can help with hints. So if there's any lingering questions about stuff, I can maybe help with that. So I think your second homework I'll post on Monday. That will cover all the stuff that we've done in the interim since. So I think the homework one ended. Was the last thing I had you doing. Yeah, so anyway, basically all the stuff we've done with Greek mathematics up till now. Okay, so last time we were covering Zeno's paradoxes, of which there are four classical ones. So we were covering kind of the most important contributors to mathematical thought from Heraclitus to Democritus. So we were at Zeno. We were discussing Zeno's paradoxes. So showing supposedly that motion is impossible. So the first one, or the third paradox that we hadn't got a chance to discuss yet, is the statement that if you consider like an arrow flying through the air, right? So this is Zeno's third paradox. So if you consider like an arrow flying through the air, so here's an arrow here. Right, flying through the air. Well, at any given instant in time, right, if you want to use more fancy notation, anything like time slice, the arrow is stationary, right? So at any given instant, the arrow is stationary, i.e. its speed is zero, right? So at any instant of time, the arrow is stationary. All right, and so this means the arrow actually doesn't move. How does it mean that? So you can think of this, right? Like imagine you use like a high-speed camera to take a picture of an arrow flying through the air. Then in your picture, the arrow seems like it's still, right? You can think of that picture as capturing an instant of time. Really, what is the confusing thing here is what do we mean by instant? What is the assumption there? Okay, so the thing being assumed here is that an instant is like a smallest indivisible unit of time. Okay, that's kind of the thing that is being attacked here. Okay. And so if we consider having a smallest indivisible unit of time that we're calling an instant, so it's like the smallest amount of time required for something to happen, right? Then at each instant, nothing is happening. Okay, the speed of this thing is zero. And so its total, its total speed is zero. Okay. So what is the idea here? So the idea is that the speed, which we'll call, the change in distance over change in time, dx dt, and I'll talk about this in a second, of course, since you've seen this. So dx dt is zero. Its speed is zero, and the idea is that the speed is zero since dx is zero. What do I mean that dx is zero here? Well, what I mean by that is at an instant in time, right, this thing isn't moving, right? So at that particular instance, right, it's in exactly one place. I can take a picture of it, right? The arrow occupies one place. So in that instant, it's not moving. So the amount of change in its position is zero at that instant. Okay. All right. So this is what Zeno is saying here. Okay. But how can this work? Well, this is fine. So this works if dt is not 0, right? Because this suddenly doesn't work if dt is 0, because you're dividing by 0 here, and this can lead to strange things, right? So, but if we assume that time, or an interval of time, consists of infinitely many equal instants, right? Okay. Then each instant has 0 duration, right? Each instant lasts for 0 amount of time. That is our definition of instant, right? Thus, dt is equal to 0. Okay. But if this is the case, well, you get some strange results, right? Because, for instance, dx dt in that case, 0, it works fine, but dx dt could be like 38, right? Because 0 is equal to 38 times 0, right? So, I mean, allowing for division of 0 like this, I could conclude that this speed is whatever I want. Okay, so obviously this is only something that I can do if this dt is not 0. Now, what is it that makes this work? What is it that makes this a paradox? So Zeno's assumption here is that time is discrete. So here's that argument about discreteness versus continuity, right? Discrete meaning that there is some smallest, right? There is some smallest finite quantum of time. So there's some smallest finite quantum of time. Okay. And then during each quantum of time, of course, this arrow would be motionless. And the reason why that has to be the case is that if it moved at all, right, there would be a time before it moved and a time after it moved, and you could split the quantum in half, right? Which means that the quantum wouldn't actually be it wouldn't be indivisible. So in this quantum of time, nothing can occur, right? This is the smallest. This is the smallest quantum of time. It can't get any smaller. It can't be divided further. And so it really wouldn't be moving in that case. Okay. And so motion would truly be an illusion if this were the case, since motion wouldn't be possible, right? You would have a bunch of slices where nothing is happening. So, I mean, all those slices taken together, still nothing is happening. So then why is motion possible? What's going on here? So this actually has to do with Leibniz and Newton, much later, right? The discoverers of calculus. So there's a reason why I specifically wanted to use the dx dt notation. So when they wrote dx dt, of course we use Leibniz's notation. Newton's notation was terrible. So Leibniz's notation was exactly this, dx dt, and he thought of this as an honest-to-God quotient where the dx and dt were infinitesimals, which you've probably heard before. Okay, what was the idea in an infinitesimal? Well, the idea is that basically you had these quantities that were small. They're infinitely small, but not 0, right? So these were infinitely small, but not 0. Okay. Now, this turns out that this is a pretty flimsy foundation here. that can be made rigorous and was made rigorous by later mathematicians. So it wasn't until the 1800s that this was made more rigorous, but Leibniz and Newton were essentially fine doing a little bit of hand waving here with this. So it turns out that, the proper way, of course, of thinking about this, instead of having to have them be infinitely small and all this nonsense, infinitely small but not equal to zero, this is contradictory. This is not solid. Again, it involves the notions of limits. Okay, and so the idea here was dx dt wasn't really an honest-to-God quotient. It was a limit of quotients. So it was a limit of a delta x over delta t as delta t goes to 0. Okay, and that way you don't have to talk about this nonsense of delta x and delta t being infinitely small, but delta t is approaching 0 here is the idea. So again, you notice that a solution to understanding what's going on is this notion of limit. Okay, this is a key thing because basically when you hear people discuss like when calculus was discovered, or when when an ancient mathematician was close to doing calculus or was close to discovering calculus, it's always about limits, because without the notion of a limit, without some understanding of that, you can't compute the quantities that you need to in calculus. So both the two fundamental things that you do computationally in calculus, right? Differentiating and integrating. Those two things are, you have to be able to compute limits to do them, right? So to compute a derivative, it's defined as in terms of limits. To compute an integral, it is the antiderivative, right? And it's also defined in terms of limits. If you go into more modern language, you can use Riemann sums, right, to define integrals. And so limits are the cutoff. Once you're doing limits, you're starting to do calculus, right? And so it wasn't until calculus was discovered that this was something, these things could be addressed. Okay, it turns out that you can actually come up with a way of tossing in infinitesimals, and it doesn't harm anything. There's a way of tossing in infinitesimals just like you toss in the square root of -1 or negative numbers. You can introduce them in the exact same way, and it's not a problem. So there's an argument for that in the textbook that I'm not going to mention. So one more paradox that Zeno discussed, which you also might have seen, is the following. So this is his last argument against motion. So you have 3 rows of people, okay? 3 rows of people or 3 rows of objects, the A's, the B's, and the C's. So the A's remain stationary, the B's are moving at some speed in this direction, and the C's are moving at the exact same speed but in the opposite direction. Okay. What this paradox addresses is the notion of an instant of time, right? So imagine that you have boiled time down into this essentially discrete quantity, okay, so that you have a smallest finite quantum of time. Okay, well, if the B's are moving in to the right at some speed and the C's are moving to the left at the exact same speed, you ask yourself the question, let's say, right, that whatever the speed is, it's at this speed, in one instant of time, a B passes an A. Okay. All right. Well, if that's the case, how long does it take a B to pass a C? Since the C's are moving at the same speed as the B's but in the opposite direction, if a B passes an A in a single instant of time, then it must pass a C in half that instant, right? But this is a problem because if an instant is the smallest indivisible, unit of time, meaning that nothing can occur having a duration less than that time, okay, well, this is a problem because you've just said that a B passes a C in half that instant. So you have, again, divided this quantum of time, which is supposedly indivisible. So that's a contradiction, right? That doesn't make any sense. And so what this says is that time is not discrete, i.e., it is a substance, right? So this was the Greek way of understanding this notion that it was a substance. It was something that was not indivisible. It had to be a substance. So you could divide time into smaller and smaller pieces. There was never a smallest quantum of time. Okay, so this is the Greek understanding from this. So these are the four classical paradoxes called Zenos paradoxes, and you see that with no technology, no machinery required, these are very good thought experiments that kind of penetrated some pretty like deep questions philosophically for the philosophy of science and what things like what these quantities like time really are, right? So these are tough, hard-hitting questions, right? That weren't appropriately addressed really until much later, right? Until almost 2,000 years later. Okay, so going back to that list, I had also mentioned Empedocles and Democritus. So Empedocles is known for a few things. So one, he showed that air is a substance. Okay. What I mean by that, and what the Greeks meant by that, was that air was not just empty, right? Air was not just a vacuum, because the the prevailing thought was that air was not necessarily a substance, right? That if you couldn't actually see something or feel something in the air, then basically nothing was going on. It was a vacuum. And so to show that air was a substance, he tossed. So he did this by tossing an inverted tumbler into water. Okay, so he tosses an inverted tumbler into water. He sees that the water doesn't immediately rush in. So that meant that there was, something in this tumbler, right? The air in the tumbler was a substance because, otherwise the water would have just immediately filled that void. So it wasn't a void. There was actually something there. So this was his way of showing that air was actually a substance. So he also had this funny addition to the primordial elements, right? So he taught that the traditional elements, earth, water, air, and fire, were like fundamental building blocks of the universe, but he added two more. So love and strife. And he had a belief that basically you could tell whether in your universe love was winning or strife was winning based on whether your universe was contracting or expanding. Okay, and so if your universe was expanding, strife was winning, and if your universe was contracting, then love was winning. And of course, it's funny now that we know the universe is expanding. So if Empedocles is right, that's we should look around to see like how much strife prevailing agrees with that. So anyway, he's also known supposedly. There's a lot of different versions of how he supposedly died. One of the versions, which I think is funny, and as I said in this course, apocryphal stories I will tell if they're funny enough or entertaining enough. It doesn't necessarily matter if there's any primary documents like addressing this. If it's funny or entertaining enough, I will tell it and let you know how supported it is. But one of the versions of how he died was to showcase his immortality. He jumped into a volcano. So yeah. Anyway, it's a pretty funny experiment. So lastly, Democritus is the last of this group of philosophers. And so you probably have heard of Democritus and his notion of atomos, or atoms, right? So he was the philosopher that replaced the notion of substances with atoms. Okay, and so he believed that you had these quantities, right? These atoms that were they were physically but not geometrically indivisible, and they were indestructible. They were constantly moving, and the space between them was completely empty. It was void. Okay, and the number of atoms was infinite, but they differed in shape and size. And so, of course, this meshes very well with a lot of what we now understand from modern physics and subatomic, especially subatomic physics. And of course, the things that he called atoms and things ultimately we call atoms, since they are ultimately further divisible, maybe the atoms of Democritus, we should reserve that. We should actually reserve that word for the subatomic particles that, are postulated to be indivisible rather than the things we call atoms. But close enough, right? We're off by like 1 degree there, so it's okay. He was also deterministic, so he also subscribed to a number of or to a deterministic philosophy, and ultimately this arose from his belief in these atoms. So Democritus believed that basically everything that happened had to happen in that way, and it had to happen in that way prescribed by like knowing essentially the motions and the interactions of these atoms. And so this is a really early example of a problem questioning. So Democritus thought that this question was answered in the affirmative, that given some initial state, given initial positions and velocities of atoms, whatever quantities you want concerning these atoms and how they behave, giving some initial set of data, you could essentially entirely deterministically predict everything that would happen if you had that perfect knowledge, right? This would later come up in a thought experiment called Laplace's demon, which we'll talk about later. But this is like the first version. This is version 1.0 of that. It is interesting to note that actually, so Karl Marx wrote his doctoral dissertation on Democritus, and the textbook thinks that it's funny to think that Marx actually wrote his dissertation on Democritus rather than Heraclitus, even though Heraclitus is kind of some Heraclitean ideas have kind of permeated some Marxist thought. So it's kind of a funny, ironic thing to note. So this is a nice like survey of kind of the important contributions in this time period. Now, starting in the like middle of the 5th century BC. So really this great Renaissance that I'm going to describe occurred after the Persians were no longer a threat to the Athenians. But so mathematics in Athens, the early days of Athenian rise to prominence began in 490 BC. But of course, this continued on for a long time. Essentially, by the time of, I'm not going to even put a time window here. We'll address that in a bit. But by the time of so circa 400 BC, Athens was going on all cylinders and had reached a level of civilization that is one of the pinnacles of human civilization prior to the Industrial Revolution, or prior to the Renaissance, I should say. Let's be a little bit more fair. Prior to the Renaissance, prior to like the 1400s, this Athenian civilization around 400 BC, and then later Roman civilization, say between like the Second Punic War and the fall of the Republic, that these are kind of like the absolute tops of human civilization in some sense. Of course, some people might fight me over that assertion, depending on where your biases lie. I admit that I'm biased in this regard, but anyway, this is to say that what was going on in Athens, starting in 490 BC and going on until the 300s, was extremely impressive. And so one of the early examples comes from Socratic dialogue. So Hippias. So Hippias was active around 420 BC and later. In fact, he's mentioned in one of Plato's dialogues. This is so he was from Elis on the Greek coast, but he basically settled in Athens. And so anyway, here's a funny exchange between he and Socrates. So I'm not actually sure what dialogue this is from, and I don't know why the light in here is so bright. Hold on for a second. Hold on. This might help. Hard to say. I think that might have made it a little less blinding. Actually, maybe not. Yep. There. I don't know. I don't think it helped it that much. Okay, so for whatever reason, this is like pretty bright. There we go. I reset somehow. Okay. So Socrates says, "And tell me, Hippias, are you not a skillful calculator and an arithmetician?" He says, "Yes, Socrates, assuredly I am. And if someone were to ask you what is the sum of 3 multiplied by 700, you would tell him the true answer in a moment, if you please. Certainly I should. Is not that because you are the wisest and ablest of men in these matters?" Yes. So Socrates was kind of teasing him about being so good at math. And the thing that Hippias did that was impressive, so he did a couple things that were impressive. So one, he discovered a curve that's called the Quadratics. Okay, so he discovered this curve called the Quadratics. The way that he described it is the following. Okay, so imagine I have unit square, which is not quite going to be a square, as most of my squares are. So let's say A, B, C, D, okay? And then imagine that this side, AD, okay, moves down at a rate of like 1 unit per second toward the side BC, okay? All right, so AD is moving down toward this side BC. Imagine that the side AB rotates about this point B at a rate of 1/4 of a revolution per second towards BC, so that after 1 second, both AD and AB coincide with BC, right? So AD is moving down, whoop, AB is rotating at a rate of 1/4 of a revolution per second, so whoop, like this, until they both coincide with the bottom of the square here, okay? At some time, t, between 0 and 1, the two moving sides meet at some point. So let an instant of time pass, right? So t being some amount of time between 0 and 1 second, right? So at that time, right, AD will have been shifted down a little bit, AB will have been rotated toward BC a little bit, and those will intersect at a point. Okay, that point we'll call P. Okay, consider the set of all those points as this motion is occurring. That the set of all those points P is called the Quadratics. Okay, So that's called the locus of all those points, or the set of all those points is called the quadratrix. Okay, so this point P that I described here, so if I've moved AD down a little bit here, and I've rotated AB a little bit so that it looks like that, okay, this point P is tracing out a curve, right? Initially they are here. This point P is tracing out some curve. Okay. All right, that curve is called the quadratrix. So what does the quadratrix actually look like? So I encourage you to look this up because I'm not going to be able to draw it nicely. The quadratrix, there's a couple of ways of expressing it. So one is parametrically. Okay, so parametrically, this is if I write this parametrically, so I have a vector valued function here, this is 1 minus t over the tangent of pi over 2 times 1 minus t. 1 minus t. That's what this thing is. Another way of expressing this, not parametrically in terms of x and y, is y is equal to x times the tangent of pi over 2y. Okay, and y is greater than or equal to 0. It's another way of expressing it. Okay, actually I'll do a quick sketch of, I'm going to do the sketch of the quadratrix that is not a function, which is why we're using parametric equations here. Because if you trace this thing out, well, either way. Yeah, I'm going to do I'll do the flipped version. It's fine. I'll do the version that is a function, actually. So if I do the flipped version of this quadratrix, what does it look like? So there's different arcs of it. There's one, and then the other branches look kind of like this. Okay, and so the quadratrix is part of one of these. And of course, which part it is depends on what quantity you've picked it. For the one that I've picked here, this is this branch, I think. It's this piece. Okay. All right. And so the quadratrix is a pretty complicated curve. What was the big deal with his discovery of this? Okay, so the big deal was that Hippias used the quadratrix to solve some classical problems. So the classical problems he solved with this were trisecting a general angle, and squaring the circle. So what are these problems? Okay, well, squaring the circle is the problem of, I give you a circle, right, of some radius, and I want you to construct a square, right, that has the same area as that circle. Okay, this is squaring the circle, if you can do that. Okay, trisecting a general angle, that's obvious. It means I give you some general angle and you cut it into 3 equal pieces. Okay, so cutting an angle into 3 equal pieces. So I take some given angle, and you prescribe to me a method for cutting this angle into 3 equal pieces. That's trisecting an angle. Squaring the circle is exactly what I said previously. It is constructing a square having the same area as a given circle. Okay. Okay. Now, Hippias used the quadratrix to solve both of these problems. Why is that such a big deal? So here is where Plato's big contribution to mathematical philosophy comes from. So for both Plato and Aristotle, their contributions to math their contributions were not, in terms of anything they did, they basically didn't do anything. Like mathematically, there's not really a single mathematical achievement that can be attributed to either Plato or Aristotle. So I mean, even just pick a random. So pick Hippias for instance. Hippias certainly contributed more mathematically than either Plato or Aristotle because he did something. I mean, he discovered this quadratics and showed how to solve these classical problems. So Aristotle and Plato did nothing like that. And Plato, the reason why Plato's influence on math at this time was strong didn't have anything to do with his contributions in that sense, but philosophically, the big way that Plato influenced Athenian mathematics and ultimately kind of the development of geometry in this way was the following. So Plato criticized this solution, or both these solutions essentially as cheating. Now, he didn't mean cheating in the violating, academic integrity sense, but he felt like it was cheating in the sense of it wasn't viewed by Plato as a proper solution. Okay, so Plato argued that any proper solution to the above questions should only include lines and circles, no other curves. So no other curves should be allowed. So it didn't matter if you could describe the quadratics entirely in terms of that motion that I described earlier, which had to do with just a motion of sides of a square. That didn't matter. What mattered was that the objects that show up in your construction, in your solution, were only lines and circles. Okay, so this seems like it seems like maybe a weird thing to nitpick on here. And so it seems like, maybe a strange choice to be so picky about the format of a solution. But philosophically, it was viewed as less pure, or Plato at least thought that it was less pure to involve these curves, and maybe it had something to do with the fact that this is a very powerful method. As we'll see, these methods involving more general curves allow you to solve all these classical questions. So trisecting a general angle is one, squaring a circle is another. The quadratics didn't have anything to do with this one, but a third, I'll write it over here. So the quadratics was involved in these two. Quadratics has nothing to do with solving this, but doubling the cube, okay, is the other very classic Greek problem, okay, of doubling the cube, and that is pretty straightforward too. I give you a cube, I want you to construct a cube that has exactly double the volume. Okay, Benz, when did the Greeks start using sine, cosine, tan? So did they need to know pi first? No. So one thing is that we developed that notation if you remember, right, we developed the notion of Sakatoa, right, which, just to remind you, if you have a right triangle, then we defined, right, if here's my angle, right, and so the hypotenuse is here, we defined, well, if this is my angle, there's the adjacent side, there's the opposite side, and there's the hypotenuse, okay. And so the sine of theta was just opposite over hypotenuse. Right, that looks like 0, so that's why you don't usually see this. Cosine would be adjacent over hypotenuse, right? And tan would be opposite over adjacent. Of course, if you recast this entirely in terms of a right triangle ABC, then really what these are is, sine theta would be, side length BC over side length AB, right? And cosine of theta would be side length AC over side length AB, and so on. And so the thing is that even if the Greeks didn't have this exact same notation that we use, they were familiar with these quantities. That's the important thing, right? Because these quantities are just ratios of side lengths, right? So again, right, to understand all of this, right, even angles, right, we understood them in terms of ratios of side lengths of right triangles. Okay, and that's why the Greeks were obsessed with being able to always handle this, right? Which is where this notion of the theory of proportion is going to come from, that I mentioned before, that Eudoxus comes up with, that the Greeks, went through a ton of trouble to develop just so that they could do algebra of, involving irrational numbers. Okay, and so, bringing back for a second this thing that I boxed. So Plato argued that any proper solution to the above question should only include lines and circles, and no other curve should be allowed. Okay. This would ultimately become the standard, and this would become the common assumptions for anyone's approach to actually solving these. So if someone claimed to have squared the circle, trisected a general angle, or doubled the cube, the assumption was that they were doing this only using lines and circles. But there's another way of thinking about this. So Plato's insistence on lines and circles as the only valid curves, to be used in solutions, to the classical problems, yields what are known as compass and straight edge constructions. Okay, so what are compass and straight edge constructions? We're going to talk a little bit more about those later, specifically, but compass and straight edge constructions are the following. The assumptions you're working with are you have a straight edge. Now, my straight edge has markings on it. It's a ruler. So imagine those aren't there. I can't use those to measure in any way. No measurement can be done using my straight edge. My straight edge is purely for the drawing of lines. It's drawing lines and connecting points. That's all I can do with this. Okay. I have a compass. What can I do with my compass? Well, I can open my compass up to a fixed distance. And what that allows me to do is compare two line segments, right? If I have a line segment here and a line segment here, and I open up my compass, I can compare it. I can transfer a length in this way. I can also use my compass to draw a circle, right? I can trace out a circle in this way. Okay, and so the lines come from the straight edge, the circles come from the compass, and those are the only things I'm allowed to use. So if I'm going to attempt to square the circle, those are the only tools I'm allowed to use, no measurement. I can only use compass and straight edge. If I'm going to trisect the general angle, compass and straight edge, doubling the cube, compass and straight edge in space, right? So these lead to some very, very interesting questions. Okay, and they are questions that are interesting and actually are very difficult. I mean, they're impossible to really make much progress on until you have more modern algebra developments. So Hippias solved those two problems, trisecting the general angle and squaring the circle using the quadratics. Another mathematician we'll talk about here in a little bit solved doubling the cube, okay, using some other not allowed curves and techniques, okay. It turns out that if you restrict yourself to compass and straight edge only, you can't do those. You cannot trisect the general angle, you cannot square the circle, and you cannot double the cube. It is impossible. The problem is that proving that it is impossible is actually difficult until you have modern algebra. Once you have modern algebra, it's not that hard to show, but it requires a ton of machinery, right? In the intervening years, there's a ton of stuff that has to be built up and developed. And so these problems that Plato originally posed basically by by restricting, by making these rules of compass and straight edge only, these problems were stated, in 400 BC and weren't solved until the 1800s. Okay, so 2200 years these were unsolved. One way or another, until it was shown in the 1800s by Pierre Wansel, showed that these were impossible. So Pierre Wansel in the 1800s, I don't remember. Well, he lived to 1848, so 1814 to 1848 showed the impossibility. The impossibility of the previous three classical problems. So the impossibility of the previous three classical problems via compass and straight edge. You can't do it. Okay, but again, it took until the 1800s for someone to actually show that this was impossible. Okay. All right. And so Hippias was very advanced, and this was extremely sophisticated stuff that he was doing. But Plato said, no, it's too good. It's too ingenious. We want to keep to the simple methods. And this in itself posed a problem that was really hard, and the Greeks spent a lot of time on it and couldn't make any progress. And the reason why is because, well, it was impossible. Okay, so nothing more fun to keep you occupied than an impossible problem. Okay, so then another thing to help you kind of understand the flow of Athenian mathematics at this time is Athenians also computed. So this was a work over. This is a work done by many people, eventually basically finished by Eudoxus, but Athenians also computed the area of a circle. Okay. So what was their approach to this? So this so multiple people worked on this. So Antiphon, this was around 425 BC. He was the first to, his idea was to use inscribed polygons to approximate the area of the circle. Okay, so how does that work? So first, you start out with a circle. Okay, and then you think of an inscribed square in the circle. So inscribed meaning the vertices of the polygon in question lie on the circle itself. So I have a square inscribed in my circle. What is known about this square? It is known, or it was known at the time of Antiphon, it was known that an inscribed square in a circle like this takes up more than 1/2 of the area. Okay, so inscribed square takes up more than 1/2 the area of the circle. Okay. How does this help? The idea is you repeat this process with polygons, say, like the octagon, right? So this is going to be a terrible picture. So there's my circle, my inscribed octagon. Looks like this. Oh, it's so bad. Oh, it is bad. Okay. But there it is. So an inscribed octagon takes up more than 3/4 of the area of the circle. And so on. And so there is this pattern. This is a square, which is a 2 squared gon. This is an octagon. This is a 2 cubed gon, and so on. Eventually, a 2 n-gon takes up more than 1 minus 1 over 2 to the n minus 1 of the area of the, so this is a fraction. It takes up this amount of the area of the circle. Okay. So Antiphon began this process, okay, but I don't think he finished this. This was something that was at least known by the time of Euclid. So this is from Euclid's Elements, this fact. And this is book 12. So book 12. Okay. That a 2 n-gon takes up more than 1 minus 1 over 2 to the n minus 1 of the area of the circle. We'll see next time how this leads to the computation of the area of the circle, because then what we do is that notice the diameter of the circle. Well, I can just connect opposite vertices, right, to get the diameter of the circle. That's the connection here. Okay, that's what gets you to computing the area of the circle. So anyway, we'll talk about that next time. If you have questions about the homework before Monday, let me know. Just email me. Otherwise, I will see you all on Monday, where we'll continue. We'll finish up most of our discussion of the Athenian math before discussing Plato and Aristotle specifically. And then I might take a little brief detour, talk about compass and straight edge constructions, and then we will be moving on. So anyway, I will see you all on Monday.